Okay, so in this video we are going to be talking about the cathode ray oscilloscope. Okay, so the cathode ray oscilloscope is mostly abbreviated as the C.R.O. Okay, the C.R.O, where C is for cathode, R is for ray, and O is oscilloscope. Okay, so this is what I want us to discuss briefly: the cathode ray oscilloscope. So the first question that we are going to start asking ourselves is that, what is this cathode ray oscilloscope? Does it have a definition? How can we define it? Well, by definition, the cathode ray oscilloscope is simply a device. It's an instrument that is used to study voltage and current waveforms of electric and electronic devices, or electric and electronic circuits. Okay, so it's a device which is used to study voltage and current waveforms of electric and electronic circuits. So examples of electric circuits that we might know might include, maybe say, a transformer, a simple generator, motors. These are examples of electric circuits. Okay, and when we are talking about electronic circuits might include things like thermistors, light dependent resistors, capacitors, and many others. Okay, so those can be examples. Transistors, those can be examples of electronic circuits, but we will come and get in depth on that. How is it that we're going to give a comparisons and differences that are there between electric and electronic circuits? But for now, we are just going to focus on this cathode ray oscilloscope. Okay, now this cathode ray oscilloscope, how can we give an introduction to it? Well, notice that the cathode ray oscilloscope involves things which we call cathode rays. Okay, the cathode ray oscilloscope involves what we like to call as cathode rays. What are cathode rays? Cathode rays are just more like streams of electrons that are released from a heated metal surface. Okay, cathode rays are just streams of electrons that are emitted from a heated metal surface. They should not be mistaken with beta particles or beta rays. Beta particles or beta rays are just simply streams of electrons that are emitted from the nucleus of a radioactive substance. Okay, beta rays are electrons which are emitted from the nucleus of a radioactive substance. All right, so what can we say now concerning this cathode ray oscilloscope? So in the next video, I'm sure we are going to get in depth to just discuss, okay, what cathode rays are and how they can be differentiated from electromagnetic rays or electromagnetic waves. Okay, so just trying to give you guys an objective. So let's get on with this now. Now, how does this cathode ray oscilloscope work? How can we explain its mechanism? How does it go about? Well, if you notice, this cathode ray oscilloscope, it has this part here which we are calling as the filament. The function of the filament here is to heat up this metal structure which has been put here, which is going to be referred to as the cathode. The function of the filament is to heat up these cathodes that we have here. There are certain instances where this same filament can be considered to be the cathode, because it's going to be very, very much heated, and there is a possibility that it can begin to emit, it can begin to release electrons. But in this case, this filament, its function is to heat up this metal structure here, which we are going to be calling as the cathode. Now, this cathode, as said, it is a metal, and if we look at the atomic composition of metals, you're going to find out that metals normally have delocalized electrons. Okay, metals normally have delocalized electrons which are not fixated in the shells of the atoms. So you're going to find out that metals normally have delocalized electrons. So upon being heated, those electrons are going to gain kinetic energy. They are going to gain kinetic energy. There will be an increase in kinetic energy, which is now going to force them to be released from the cathode. Okay, these electrons, upon being heated, upon gaining kinetic energy, they are going to be released from this cathode metal that we have here. So what is going to happen is that these electrons are going to be emitted. They're going to start being released. Okay, these electrons are going to start being released. They will begin to move. They will gain enough kinetic energy to be released from that cathode metal that we have here. Now, one thing that you need to understand is that anytime cathode rays, anytime these stream of electrons are released, they always move in straight lines. Okay, that's one property that you need to understand about cathode rays. They always move in straight lines. So once they are released here, we're going to see that they are going to enter into this domain, into this structure here, which we are calling as the brightness control grid. Okay, they're going to enter into this domain, into this structure, metallic structure, which we are simply referring to as the brightness control grid. Now, one thing that you need to know is that the brightness control grid is always supplied with a negative voltage. Okay, the brightness control grid is always supplied with a negative voltage. In other words, the brightness control grid is negatively charged. Okay, the brightness control grid is negatively charged, and its negativity can be varied. When I say that its negativity can be varied, I mean its negativity can either be increased or reduced. Okay, when I say that its negativity can be varied, I mean that its negativity can either be increased or reduced. Okay, so what exactly is the function of the brightness control grid? Well, when these electrons have been released, what happens is that they tend to move within this cathode ray oscilloscope, and they tend to strike this part which we're simply referring to as the fluorescent screen. Okay, the fluorescent screen. And as they are hitting, as they are moving, when they hit this fluorescent screen, what you need to understand is that there are some certain spots which are formed on the screen. Okay, so it is the function of this brightness control grid to now control the brightness of those spots which are going to be formed on that same screen. It's the function of the brightness control grid to control the brightness of those spots which are formed on this fluorescent screen as these electrons strike it. Okay, as these electrons strike it. So what is now going to happen is this: once they begin to pass through this brightness control grid, let me explain to you what happens. We have said that the brightness control grid is negatively charged. These cathode rays, remember, we're saying that these are streams of electrons and they are also negatively charged. The first law of electrostatics states that like charges repel, but unlike charges, what do? They attract. So because the brightness control grid is negatively charged and these electrons are also negatively charged, what begins to happen is that as they are passing through this brightness control grid, they begin to experience some repulsion. Okay, they begin to experience some repulsion. So here's the thing: if the negativity of the brightness control grid has been increased, there will be a lot of electrons that are going to be repelled. Okay, if the negativity of the control grid has been increased, there will be a lot of electrons that are going to be repelled. As a result, the brightness of the spots which are going to be formed on the screen will reduce. Okay, will be low. But if the control grid has been made to be less negatively charged, you're going to see that a lot of electrons will pass through. A lot of electrons will be allowed to flow, to move through. Why? Because its negativity has been reduced. The electrons which are passing here will experience less repulsion. Okay? They will experience less repulsion. So, once a lot of electrons pass through here, what is going to happen is that the brightness of the spots which are going to be formed on the screen will be high. Okay? It will be high. So, one more time. If the control grid has been increased negatively, what is going to happen is that a lot of electrons here are going to be repelled. As a result, the brightness of the spot which is going to be formed on the screen will be low. But if its negativity has been reduced, a lot of electrons will be allowed to pass through, a lot of electrons will be allowed to move through, and the brightness of the spot formed on the screen is going to be high. Okay, it's going to be high. Now watch. Once it passes through the brightness control grid, you're going to see that it's now going to step into the anode. Okay, it's now going to step into the anode. Now this anode here serves two functions. Okay, so we have a cathode and we also have an anode here. Now the anode serves two functions. The first one is to focus the electrons together. Its function is to focus the cathode rays. Apart from focusing them, apart from compressing them, like bringing them together, its other function is to accelerate these cathode rays. Okay, so it does not only just focus the electrons, but it also accelerates them. It is for this reason that the anode can also be called as the focusing and accelerating. It is for this reason that it can be called as the focusing and accelerating electrode. Why? Because it serves two functions. It focuses the electrons. To focus means to compress them. It's more like bring them together. Have you seen how scattered they are, right? When they begin to pass through the anode, it's like they'll be made to move more closer to each other. It will converge them. It's like they'll begin to move much closer to each other. It's more like trying to focus them, trying to bring them together. Okay, and as it is doing that, it is also accelerating them. When I say accelerating them, it's simply increasing their velocity, it's simply increasing their speed. Okay, now before I proceed to the Y plates and the X plates, one thing that you need to know is that this part of the cathode ray oscilloscope that I'm just from explaining, which includes the filament, the cathode, the brightness control grid, and the anodes. This first part of the cathode ray oscilloscope is what you might call as the electron gun. Okay, this is what you might refer to, or this is what you might call as the electron gun, because it is on this part where we're seeing electrons being released. This is the part where we're seeing electrons being fired from, and they are passing through this cathode ray oscilloscope, as we have seen. Okay, so this part is going to be referred to as our electron gun, so don't forget that. Okay, now another part or another property of cathode rays that you need to know, so I hope you're following. One, we said that these cathode rays are negatively charged. Okay, apart from saying that they are negatively charged, we said that there are also streams of electrons. The fact that they can also move shows that they possess kinetic energy. Remember, according to physics, any body, any substance that is in motion tends to possess kinetic energy, tends to exhibit kinetic energy. So the other property of cathode rays that you need to know is that they also have kinetic energy. And also not forgetting, they also travel or move in straight lines. Okay, they also travel or move in straight lines. So don't forget that. Now, when we reach this part now, this is where we're now seeing the Y plates and the X plates. So this new part which we have reached here, okay, which includes the Y plates and the X plates, this part here, this is what you might call as the electronic, or rather, let me not say electronic, this is the electrostatic deflection system. Okay, electrostatic deflection system. Electrostatic deflection system. In case maybe the electrostatic word goes, at least just try to know that this is the deflection system. Okay, this is going to be referred to as the deflection system. So we have the electron gun. Electron gun includes the filament, the cathode, the brightness control grid, the anode, or better say the focusing and accelerating electrode, which describes its function. And this part here, this is what is going to be referred to as the deflection system. The function of the Y plates is to deflect the electron beam or the electron rays horizontally, rather not horizontally, let me say vertically. Okay, so the function of the Y plates is to deflect, okay, these electron beams, these electron rays which are passing through here vertically. Okay, just look at it. Look at the way these metal plates are even positioned in. Okay, they are positioned in such a way that they are going to be deflecting, okay, the cathode rays, these electron rays vertically. There is a certain alternating current which is supplied to these Y plates, causing these electrons to start moving into this vertical way, okay, into this vertical way. The function of the X plates, on the other hand, is to deflect, okay, these cathode rays horizontally. Okay, so just look at it. Y plates, X plates. If we try to relate this to mathematics, you're going to see that the y-axis is going to be in this way, and the x-axis is going to be in that way. This is where even these names tend to come from, that is Y plates, X plates, because the Y plates deflect these rays, these electrons vertically, just like the y-axis goes. And then the function of these cathode rays, or rather the X plates, is to deflect, okay, these cathode rays horizontally, just more like in the x-axis. Okay, so I want to show you some certain diagrams which I really want you guys to understand. So take note, the Y plates vertically, they deflect the electron rays vertically. The X plates are going to deflect those cathode rays horizontally. Now here's the thing, when the Y plates are switched on, okay, and the X plates are switched off, all right, the way that the way those electrons, those cathode rays, that electron beam, the way it's going to be moving, it's going to be moving in this way. You need to memorize these diagrams, they're very important. So imagine this is like your screen, you're trying to look at it from here, okay, like just in front here, you're trying to look at it. When the Y plates are on and the X plates are off, that electron beam is going to be moving in this way, okay, it's going to be moving into this vertical way. So this is for the Y plates, this is for the Y plates. That is, if the Y plates are on and the X plates are off, okay, when the Y plates are on and the X plates are off. And please also know this, don't try to follow that rule of the alphabet, like X plates are always supposed to come before the Y plates, that is X, Y, Z, so X comes first before Y. Don't try to follow that. Under the cathode ray oscilloscope, it's the Y plates, okay, and then the X plates follow after. So that's what we're going to have. So when the Y plates are on and the X plates are off, this is what we're going to have. Conversely, if the X plates are the ones which are on, that is, if it's the X plates alone which are on and the Y plates are off, when the X plates are on and the Y plates are off, what we're going to have is this. So your electron beam is going to be moving horizontally, like we had established, right? Horizontally. So this is how they're going to be moving. So they're going to be going in this way. Okay, so this is what you're going to have on your screen if the X plates are on and the Y plates are off. But the question is, what if we switch them both? What if the Y plates were on and the X plates are on? What if we were to switch them on together? When they are switched on together, that is, when the X plates are on and the Y plates are on, your electron beam is going to be moving in a wavy way. Okay, it's going to be more like in a wave way, in a wave kind of motion. They're going to be moving in a wavy way. They're going to start forming waves. So when your X plates are on, okay, when your X plates are on and your Y plates are also on, okay, these are going to be moving in form of waves. Okay, it's going to be in the form of waves. That's how it's going to be going. Okay, yeah, that's how it's going to be going. It's going to be in a wave kind of way. Okay, it's not that much better, but just try to have this idea that it kind of moves in a wave kind of way. So in some other videos, as I will be talking about problems or questions which are given under the cathode ray oscilloscope, I'll try to show you that we don't just end here in showing how the beam is going to be moving. So a beam is just more like a group of rays. We don't only just end up in just trying to show how these waves are going to be moving in the direction. There's some certain calculations which are made, calculations involving something which we call peak voltage. Apart from peak voltage, but there is also something which is referred to as the time base, and I'll come and show you how we handle that. So for now, this is what I can say about the cathode ray oscilloscope. Oh yeah, and one more thing. The cathode ray oscilloscope is a vacuum. There is a vacuum inside here. I mean, there shouldn't be any air molecules that should be present in this device as these electrons are flowing in, because these electrons, if there are some air particles, air molecules here, these electrons will begin to collide with those air molecules, and I mean, once they begin to collide, you're going to find out that not all of them may reach this fluorescent screen as expected. So to avoid any disturbances, we always try to make this cathode ray oscilloscope a vacuum. Okay, we always try to make this cathode ray oscilloscope a vacuum so that these electrons should not experience any collisions, okay, or resistance as they are flowing like that. So that's what we can say on the cathode ray oscilloscope. Thank you.